Merge sort is a sorting algorithm. It takes as input an array whose values are in an arbitrary order, and it outputs an array with the same elements in increasing order of values. Merge sort is in some ways a little bit like a traffic jam on the freeway caused by a disappearing lane, because the core of the merge sort algorithm resembles cars merging into a single lane. Completely unlike a traffic jam, merge sort is extremely fast. It is guaranteed to have a time complexity of theta of n log n in the worst case, which is known to be the best possible time complexity for comparison-based sorting algorithms. It is also cache-friendly, making it ideal for modern computers. In fact, the only downside to merge sort that I can think of is that it is not usually in place. It uses additional memory for processing in the form of a temporary array or two. If you would like to learn about an in-place algorithm with an average time complexity of theta of n log n, check out our tutorial on Quicksort. Find the link in the upper right corner of the screen. Stay with this video to understand how merge sort works under the hood, how to implement it in the C language, and how to understand its time complexity using a beautiful graphical argument. Let us take a look at how merge sort operates. Merge sort is typically implemented as a recursive algorithm, with the recursive calls sorting subranges of the input array. Initially, merge sort splits the input array, called T, into two ranges of roughly the same length. Then it calls itself on the range on the left-hand side. The recursion magic makes the range sorted. It then calls itself on the other range. And recursion magic again makes sure this range is sorted. At this point, we have two ranges that are sorted. We need to merge these ranges together, which is what gives the algorithm its name. To merge the two ranges, we use additional memory in the form of two temporary arrays called L and R. We copy each range into its own temporary array. We forget for now the contents of the array T, as it will be overridden by the merging. We fill in the array T from left to right, with the elements in increasing order. To do this, we use 3 pointers, each into one of the 3 arrays. Everything strictly before the pointers into the temporary arrays has already been processed and stored into the array T. The pointer into T indicates the next position in T that we should fill in. The idea is that all elements that have already been placed into T are smaller than all elements that remain to be processed in both L and R. What remains to be done is to merge the remaining elements of L and R into the space remaining in T. The current elements in L and R compete for their place in the array T. At each step, the smaller of them wins and is positioned in the next place available, and the pointers are updated accordingly. Initially, all 3 pointers point to the first element into each array. We compare the current elements in L and R. As L and R are sorted, the smallest value overall must be either the first element in L or the first element in R, whichever is smaller. We copy this smaller value into T and update the 2 pointers as needed. We keep going for as long as the pointers into L and R point at valid elements. Compare 6 and 3 and choose 3. Compare 6 and 4 and choose 4. Compare 6 and 8 and choose 6. Compare 7 and 8 and choose 7. At this point, the pointer into L points to an element just past the contents of L. This means that we have finished processing L. It remains to copy the rest of the values in R into the array T. We are done with merging the 2 subranges and we have obtained the sorted array. Let's implement merge sort in the C language. We start with the main function, called sort, that takes as input an array T and its size, n, and sorts the array. As merge sort is recursive, and recursive calls sort subranges of the initial array, we need an auxiliary function sort_range. It sorts a range of the array T, given by the index of the first element, f, and the number of elements in the range, n. The function sort then simply calls sort_range for the entire array. As with any recursive function that terminates, sort_range must have a base case where recursion is not necessary anymore. The base case consists of ranges having 0 or 1 elements, as these ranges are already sorted. In the base case, there is no work to do. Instead, we perform all the hard work in the recursive case. We need to split the range into 2 subranges of roughly the same size. The length of the first subrange is half the length of the initial range, rounded down to the nearest integer. The length of the second subrange is then the initial number of elements, minus the elements in the first subrange. We sort recursively the first subrange. We sort recursively the second one as well. Once the 2 subranges sorted, we merge them together. We need a separate function that performs the merging. We finish off the sort_range function by calling merge for the 2 subranges. Going back to merge, we first allocate on the stack 2 temporary arrays. We are using here a language feature of the C language, introduced in the standard C99, which allows us to declare variable length arrays. If your compiler does not support this, or if you are short on stack space, you may want to declare L and R as global variables. Alternatively, and slightly better, you may want to allocate them in the function sort and pass them around as parameters. Independently of how we allocate the temporary arrays, the algorithm proceeds in a similar manner. We copy the two subranges into the temporary arrays. We initialize the 3 pointers as discussed earlier. We loop for as long as both pointers into the two temporary arrays are valid. We check which of the current elements in L and R is smaller. If the current element in L is smaller than the one in R, we add it to T, and increment the pointers into L and T. If the current element in R is smaller, we add it to T and increment the pointers into R and T. As either J or K increases at each loop iteration, at some point one of them will point just past the end of the respective subrange. This makes the looping condition become false and the while loop therefore terminates. At this point, one of the two subranges has 0 elements left in it to be processed, and the other subrange has 1 or more elements. What remains to be done is to copy the non-empty subrange into T. There is no need to check which one is non-empty, we can simply copy both of them, as copying the empty subrange has no effect at all. Let's now try to understand why merge sort is so efficient. Merge sort has a guaranteed worst-case time complexity of theta of n log n. It is quite easy to understand why, by using a graphical argument. But first, we must concentrate on the merging operation. The declarations run in constant time, independent of the input data. The running time is therefore dominated by the loops, whose running times depend on the input data. The bodies of the first two loops execute in constant time. Therefore, the running time of the loops is proportional to the number of iterations, which is n1 for the first loop and n2 for the second loop. Therefore, the first loop executes in theta of n1 and the second in theta of n2. As n1 plus n2 is n, the first two loops take theta of n time. The bodies of the 3 loops below also execute in constant time each, so it is sufficient to count the number of iterations of these loops. In the main loop, either j or k increases at each step. As the loop stops when j hits n1 or k hits n2, there can be at most n1 increments of j and at most n2 increments of k. Therefore, the body of the loop executes at most n1 plus n2 times before finishing, which means the loop has a running time of big O of n. Using a similar argument, the second to last loop executes at most n1 iterations, and the last loop at most n2 iterations, which adds up to at most n iterations in total for the last two loops. Adding up the running time of the various parts, we obtain that the running time of the function merge is proportional to n. Now that we have cleared up the time complexity of merge, let us go back to the main recursive algorithm. For n less than or equal to 1, things are easy as the running time is constant. For n greater than 1, we represent the running time graphically, using tokens, with each token accounting for 1 unit of time. We start with the call to sort underscore range for the initial array and place the tokens representing its running time inside the rectangle. The running time is the sum of 3 components. The running time necessary to sort the first range, which we represent in this rectangle. The running time necessary to sort the second range, which we represent in this rectangle. And the running time necessary to merge. As discussed earlier, merging takes time theta of n, so we put in n tokens for merging. It remains to add tokens for the recursive calls. To do this, we concentrate on each of the 2 subranges in turn. This call to sort underscore range also consists of 2 recursive calls for the 2 sub-ranges, and a merge, for which we put in as many tokens as the size of the sub-range. Similarly, the second recursive call has the same structure. We repeat this process until we obtain ranges with 0 or 1 elements, for which we place 1 token. It remains to count the number of tokens to obtain our running time. There are n tokens horizontally on each row. The challenge is to count the number of rows. Each row has subranges approximately half the size of the subranges in the row below. The number of times we can split an entity in half until it reaches a size of 1 is the definition of the function logarithm. Therefore, there are about log n rows. We now count the number of tokens. There are n tokens horizontally times about log n tokens vertically, which amounts to a grand total of about n log n tokens. As each token represents a unit of time, we conclude that the algorithm has a time complexity of theta of n log n. Subscribe to the Truly Understanding Algorithms YouTube channel by using the button in the middle of the screen to stay up to date with our videos that help you better understand interesting algorithms and data structures. Give us a thumbs up and leave a comment with topics that you would like us to cover in the future. Also visit trulyunderstandingalgorithms.com to read a textual version of this tutorial.